Hi, I'm Miss Mixell, and I'm one of the material science engineering teachers at Eagle Crest. This podcast is going to focus on quantitatively calculating Young's modulus. So, our essential question for today's podcast is what's the mathematical equation that represents Young's modulus, and what does the Young's modulus value represent? So, if we start to dive into the mathematical equation, there's a couple of different components that go into it. Stress is the load or force applied to a material that results in strain. So, to calculate the stress, you're going to divide the force by the cross sectional area. So, stress is equal to force divided by cross sectional area. And just a reminder, force and pressure are not the same things. You might remember that force is your mass times acceleration due to gravity. On Earth, that's always 9.81 meters per second squared, whereas pressure is force divided by area. So if we consider force divided by area or pressure, that is why if someone steps on you in an athletic tennis shoe, it's going to feel a lot different if they step on your toe with a high-heeled shoe on. We can see in an athletic tennis shoe, you have a much greater area that your force, your mass times acceleration due to gravity, is being applied to. Whereas if you're in a high heeled shoe, all of that force is being applied to a much smaller cross sectional area, right? And thus you would feel a much, much, much higher amount of pressure, 600 newtons per centimeter squared, compared to if someone stepped on you with an athletic shoe, where you'd feel a pressure of 2 newtons per cubic centimeter. So if we look at how we experimentally calculate tensile stress, again, we can take an iron rod, cross-sectional area of 2 meters squared, and if a tensile force of 500 newtons is being applied to it on both sides of the rod, as shown, it's being stretched or pulled in both directions with the force of 500 newtons. To find the tensile stress, we're going to take the force divided by the area, force being 500 newtons, area being 2 meters squared, which would give us a stress value of 250 newtons per meters squared. Our second component that goes into calculating Young's modulus is strain. Strain measures how much deformation occurred. That can be elastic, bonds being stretched, but when the force is removed, it returns to its original position, or plastic deformation, where bonds are broken and the change is permanent. So to calculate strain, we're going to divide change in length by original length. Again, our equation for strain is change in length divided by original length. So again, we could do this experimentally. If we consider our 2-meter long iron rod, the tensile force acting on the rod elongates it by 0.02 meters. And so to calculate the strain, we would take the extension, or the difference in length, 0.02 meters, and divide it by the original length of the rod, which was 2 meters. Our strain value is going to be 0.01. And note, meters divided by meters, the meters will cancel out. And so your strain value is always a numerical value that does not have a unit, because in order to calculate it properly, your 2 units should match and cancel out. Finally, we can put stress and strain together to calculate Young's modulus. Young's modulus, abbreviated as capital E, is stress divided by strain. So stress divided by strain, which essentially means it's force divided by area over change in length divided by the original length. So let's look at why it's so important to calculate Young's modulus. Here's an example that happened just a year ago. This is in Pittsburgh, Pennsylvania on January 28th, 2022. You're seeing drone footage from a bridge that collapsed there. Young's modulus allows engineers to know how materials behave. We can measure the properties, specifically the mechanical properties of a material, and know its behavior. That allows us to use proper selection of materials as we design things. And it allows engineers to calculate stress and understand lifespan and when something will fail, preferably before failure actually happens, which was not true in this case. Okay, we're going to solve a couple of problems in your notes. So I would encourage you to take a second and write down this problem set into your notes along with the table below, and then we'll walk through and use our Young's modulus equation to solve it. A 60 kilogram block hangs on a wire with a cross-sectional area of 2 millimeters squared. The wire was originally 4 meters long, but stretches by 3 centimeters under the applied load. Calculate the Young's modulus value of the wire. So to start with, we're going to need to fill in our data table with our givens or our measurements that we collected. 60 kilograms should be our mass value. Cross-sectional area is 2 millimeters squared. Our original length, L0, is 4 meters, and we stretched by 3 centimeters, so our change in length is 3 centimeters. So again, we're going to look at what those measurements give us and fill that in on the table below. And then our next step is going to be to convert to the correct units so we can do the stress and strain calculation and then put those together to get Young's modulus. So we need our delta L, or our change in length, to be in meters. One of our first conversions is going to be to convert from centimeters to meters so that we can use the initial length and the final length as part of our calculations. They need to be in the same units. To convert to meters, we're going to take centimeters and recognize that there's 100 centimeters in 1 meter. So if we take 3 centimeters and multiply it by 100 centimeters 1 meter over 100 centimeters, we can see centimeters will cancel out. Our answer will be in meters now. So we get 0.03 meters. The other conversion we need to do is we need to get from millimeters squared into meters squared. And so to do that, since we're in squared, millimeters times millimeters, we're going to have to take millimeters and divide it by 1,000 millimeters is 1 meter twice, because millimeters times millimeters will cancel with millimeters squared. And that'll convert our answer to meters times meters, or meters squared. So on our calculator, we'll take 2 times 1 times 1, divided by 1,000, and then divided by 1,000 again. And we can see our area in meters squared is a very small value, 0.00002 meters squared. Okay, our last calculation is that we need to make sure that we take our mass and turn it into force. So we measured in kilograms, but in order to use our equations, we need to know not mass in kilograms, but force in newtons. You might remember that force is mass times acceleration due to gravity. So we're going to take our mass value in kilograms, 60 kilograms, and multiply it by acceleration due to gravity, which on Earth is 9.81 meters per second squared. Kilograms times meters over second squared is equivalent to a newton. So our value in newtons, 60 times 9.81, becomes the 588.6 newtons we see in the table. We are now ready to calculate our strain and our stress. So to calculate our stress, we're going to take force divided by area. Force in newtons, 588.6, we got that value right here, divided by our area in meters squared, the 0.00002 meters squared, and we get a value of 294,300,000 newtons per meter squared. Now to calculate strain, we're going to be taking our change in length and dividing it by the original length. So delta L divided by original length. So our change in length is 0.03 meters divided by the original length of 4 meters gives us a value of 0.0075. Again, this number is unitless because meters cancels with meters. So now our final step is going to be to calculate Young's modulus. To do that, we're going to need to pay attention to our strain value and our stress value. Because if you remember, E, or Young's modulus, is stress divided by strain. So we're going to take our stress value, the 294,300,000 newtons per meter squared, and divide it by our strain value, or the 0.0075. When we do that, we're going to get a Young's modulus value of 3.924 times 10 to the 10th newtons per meters squared. Okay, so now we're going to shift and work on solving Young's modulus problems from word problems instead of from experimental data sets. So here's our first problem. Again, I'd encourage you to write this down into your notes. During a windstorm, a telephone wire is under a stress of 3 newtons per meter squared. The strain of the wire is 6.23 times 10 to the negative ninth. What's the Young's modulus value for the wire during the storm? So to solve for this, we're going to be looking at Young's modulus, solving for E, which is stress divided by strain. We don't have to use the more extensive equation over here to the right because it already gave us in the world problem the stress and the strain value. So knowing we take stress divided by strain, we have a stress of 3 newtons per meter squared, and we're going to divide it by the strain, 6.23 times 10 to the negative ninth. And so when we fill in the stress divided by the strain and plug that into our calculator, we should get a value of 4.81 times 10 to the 8th newtons per meter squared. Again, that would represent the Young's modulus, or the stiffness of the wire during the windstorm. All right, let's try a second problem. Again, I would take a second, pause me, and write this problem into your notes. A patient's leg was put into traction, stretching the femur, ooh, that doesn't sound comfortable, from a length of 0.460 meters to 0.462 meters. The femur has an area of 0.0023 meters squared. If a force of 3.29 times 10 to the 7 newtons is used to stretch the femur, calculate the Young's modulus value. So we're going to start by identifying our givens, and we can see we're going to need to use the more extensive Young's modulus equation, force divided by area over delta L divided by original length. So let's start by identifying our givens. We know that the force is 3.29 times 10 to the 7 newtons. Our area is 0.0023 meters squared. Our change in length is the difference between our original and final measurement, or 0.002 meters. And our original length is 0.460 meters, our starting length of the femur. So now that we have those values, we are going to take force divided by area, and that gives us our stress value, and delta L divided by original length, which gives us our strain value. Once we've solved for stress and strain, we can plug them into the equation to calculate the Young's modulus. Stress divided by strain will give us a Young's modulus of 3.29 times 10 to the 12th newtons per meters squared. I hope this podcast was helpful. Thanks for watching.